Okay, so here we go. Just only a couple minutes behind, so it's not too bad. So the last time we actually had lecture was on Friday of last week. And on Friday last week, we looked at 4 examples that concerned estimation and sample size collection via a systematic sample. So as a reminder, sorry, 1 second. Okay, so as a reminder, our systematic sampling approach is effectively an alternative to the simple random sampling approach that is best utilized, or that is ideal in situations where we can't observe a sampling frame. So the systematic sample is essentially an approach where we would just select 1 in every K person to be a part of our sample. Now, through this approach, we are able to construct estimates for a mean, a total. We are able to bound those estimates using confidence intervals. We are also able to construct estimates for a proportion, bound that estimate, and we can do sample size collection in each of those different situations. What we're going to talk about today is an extension of systematic sampling that is called repeated systematic sampling. And repeated systematic sampling is very similar to systematic sampling, except that instead of collecting 1 large systematic sample, we collect n subscript s smaller systematic samples. So we're working with the same population. The idea of how we collect our information is exactly the same. We just move through every kth person and we let them be a part of our sample. But now we stagger the start point k times as well. And in the end, what we end up with is ns systematic samples that we can utilize for estimation of the mean, total, and we can bound those. And we can also use this information to estimate rho, but we'll come back to that point in a little bit. Okay, so same overall objective. It's an extension of systematic sampling. The goal in the end is to estimate some population quantity, say a mean, a proportion, a total, whatever. Okay, so as an example, suppose that we wanted to collect one in 5 systematic sample from a one in 5 systematic sample where we end up with little n is equal to 60 as our sample size. Okay, we could take another approach where instead of doing 1 in 5 systematic samples to get a sample size of 60, we do say 10 1 in 50 systematic samples where each sample contains 6 measurements. So in the end, we still end up with 60 observations, but the way that our observations are structured are across 10 different samples now. Okay. From these 10 samples, as I mentioned before, we can do the same things that we had done previously. So estimate a mean, estimate a total. And really the only difference here is that we have to stagger the start point. So we would start at K, or at K prime rather, then we would multiply by 2, and that would be our next starting point, multiply by 3, that would be our next starting point, etc. So the overall process is exactly the same, except that our 10 samples are going to have observations that are spread a little bit further apart than they would have been in the traditional case. And the structure, the way that we view the data will be different as well. So our estimates will look slightly different, but really they're going to be computed in the same way. Okay, so to further illustrate this idea, suppose that we want to collect a sample of size 50 from a population of size 950. In this situation, instead of collecting just 1 systematic sample, we're going to collect 10 1 in K prime systematic samples. Okay, so how can we go about doing this? All right, so first, we can write out what our K prime is going to be. So K prime is going to be essentially the sampling ratio for the first sample. Okay, so first we're going to declare K to equal capital N over little n. So this is the same declaration we had before. and this is going to give us 19. Okay, second, we declare k prime to be equal to little ns multiplied by k, which is 190. Okay, so the k prime is going to be effectively our sampling ratio, or the space between each observation within each of the 10 systematic samples. All right, and then third, we select 10 starting values between 1 and k prime. Okay. All right, so for example, we could have, maybe I can rate it laterally like this. So if these are the 10 samples down the side here, so this will be sample, and you'd have 1, 2, 3, 4, 5, 6, 8, 9, 10. You'd have observation 1. So the starting point is going to be one of those randomly selected numbers between 1 and 190. So for example, you could have something like 59, 128, 13, 97, 16, 6, 118, 96, 125, 66. Okay. And then our second observation for each sample is going to be this plus 190 in that case. So for example, here you would have 249, right? And then you would just continue until you fill each of the available slots within the sample. Okay. So any questions on that concept? Okay, so in general, the suggestion is to use at least 10 of these repeated systematic samples. So instead of if we're going to use repeated systematic sampling, the suggestion is to use 10. We're going to look at a situation later where we don't have that many, but for illustrative purposes, we'll see how we could use the information to compute an estimate for rho. But again, we'll come back to that point in a little bit. So really, I mean, the suggestion is to use 10, but obviously there's going to be restrictions on how many systematic samples we can actually collect from a given population, or how many repeated systematic samples we could collect from a given population, depending on the size and the number of observations that we would like to collect. But we can always try and structure it so that we have 10 of these samples. But if the compensation for that is maybe each sample only has 2 or 3 values in it, then you might need to consider a different strategy. So there's there's obviously a restriction depending on the values of capital N and little n that we are going to work with. All right, so again, from the repeated approach, we are able to construct estimates for a mean and a total. Okay, and these are going to be designated. So we're still estimating the population mean, we're still estimating a population total if we want, and then we can bound those estimates. So from the repeated systematic sampling approach, we can say that mu hat for the repeated systematic sample is equal to 1 over little ns, the sum from I equals 1 to little ns of the mu hat sy times I. So basically, our estimate of the average is just the average across all of the observations in the sample anyways, except that we write it as the average of the averages from each systematic sample. But this converges to the same value. So it's the same effect. It is the same estimate that we saw in the traditional systematic sampling approach, which is the SRS estimate. It's just written using a different formula. The estimate for the variance of mu SY, or mu RSY in this case, is equal to 1 minus little n over capital N of sigma squared mu hat over n subscript s, where sigma squared mu hat is equal to the sum across all repeated systematic samples of each mean minus the grand mean squared divided by ns minus 1. Okay, so basically the estimate for our variance term when we use repeated systematic sampling is the between repeated systematic sampling variance estimate from all of the samples. So instead of taking each observation and subtracting the mean and squaring that and dividing by n minus 1, which is the traditional estimate of variation, we are now considering effectively what is the between systematic sample variance. So we're taking each of the means from each systematic sample and subtracting the estimate of the grand mean across the entire experiment and squaring that. So this is actually a variation that you would see within an ANOVA situation. So if you recall, and we'll see an example of this in a bit, but you might recall that in ANOVA, we have a total variation term, which is the square differences between each observation and the mean for the entire sample that we're working with. And we decompose that into two types of, or we decompose that total variation term or total sum of square term, that's actually what it is, into two types, which is the between systematic sample sum of squares and the within systematic sample sum of squares. And this is actually the between systematic sample sum of squares. Okay. So from this, of course, estimating the total would be done in the normal way. We just have to multiply by our population size. Okay, so let's look at a few examples. So suppose that we collect 10 systematic samples from the same population. The population size is 400, and in the end, we wanted to collect 80 observations in total. So we have 10 samples. Each sample should have 8 observations, but we can show that this is true as follows. All right, so in part A, well, first off, what are we looking at in the table? So in this table, we have an estimate for the mean of each systematic sample. So from this population, we have collected 10 systematic samples, which are the sample values 1 through 10 given above. And these values here, so the 3.75, the 3.38, the 2.88, the 4.62, the 4.5, etc. Those are the means of each systematic sample. So in part A, we're asked, determine the number of observations per systematic sample. All right, so this is actually pretty straightforward. So we would just have little n. Maybe we shouldn't use, we'll call it little n sy comma I. So the number of observations in the ith systematic sample is going to be equal to little n, the total number of observations collected, divided by little ns, which is the number of systematic samples, right? And this makes sense. So we have collected 80 observations in total. We have divided the 80 observations across 10 systematic samples. So that gives us 8 observations per sample. So each of the means given in the table above, so for example, mu hat sy1, right, is the average of 8 is the average of 8 observations in systematic sample 1, right? And then the 3.38, that would be the average of the 8 observations in systematic sample 2, etc. Okay, in part B, we're asked to estimate mu, which represents the average number of people per car in each sample. Okay, so mu hat, and we can use our repeated systematic sampling estimator here. So actually we can just write this as mu hat, I guess. Well, let's be consistent. So mu hat RSY estimates mu. This should be mu tilde RSY. The symbolage in this class. Okay, so then we have mu tilde RSY is equal to the sum from I equals 1 to NS, which is going to be 10 in this case, of mu hat systematic sample I, and then this whole thing is going to be over NS. Okay, so effectively all we're doing here is we're adding the 10 means from the table above together, and then we're dividing by the number of samples. So this is going to be 1 over 10 multiplied by 3.75 plus 3.38 all the way up to 4.38. So here, I'll just get rid of this middle one so that I have a little bit more room. Right. And then this should give us 1 over 10 multiplied by 41.63, which is equal to 4.163. Okay. And then finally, it says estimate the variance of mu hat RSY, where sigma squared of mu hat is equal to 0.455978. Okay, so we can start off 1 over little n minus capital N is equal to 1 minus 80 over 400. All right. So this is going to be 1 minus, divided by 40 is 2 over 200. Divided by 2 is equal to 1 over 100. Is that correct? No, there's no way that's correct. Simple math, right? Divide by 40 is 2. Divide by 40 is 10. So that's 2 over 10, which is 1/5. 1 minus 1/5 is 1 minus 0.2, which is 0.8, right? So this is 1 over a fifth, which is equal to 0.8. Therefore, use FPC. Okay, so then we're going to have the variance of mu hat RSY is equal to 1 minus little n over capital N sigma squared mu hat divided by NS. So this will be 1 minus 80 over 400 multiplied by 0.455979 divided by 10, which is 0.036477831. All right. So hopefully what you're starting to notice, at least through the first lecture set, is that the estimation procedures that we're using are very similar across the different approaches. All we're really doing here is just slightly changing the formula, mainly for the variance. The estimate of the mean is pretty consistent across any type of sampling approach. I mean, you're effectively just taking an average from the information that you have collected. But the variation estimate is changing depending on how we collect the information. The way we use the FPC is the same. And in the end, what we're looking for are, ideally smaller variations that imply that we have more precise estimates given that they are unbiased. Okay, so illustrative example of how our repeated systematic sampling approach could be used to estimate a mean. Let's talk a little bit more about the variation of the estimate. So as I had mentioned before, we can actually consider the sigma squared mu hat term to be the between systematic sample sum of squares, or the between systematic sample variance. Now, this idea is an idea that comes out of an ANOVA type experiment. So let's imagine that when we collect our information, we arrange it in a table that looks like the one given on slide 70. So this table is showing us the systematic sample number, which ranges from 1 to k, and then it's showing us the observations for each sample, and it's giving us the mean within, or the mean for each systematic sample. So you could imagine here that at the end, for example, you would have some grand mean for the entire experiment. We can compute the difference between each observation and the grand mean. We can square that. We can take the difference between each observation and its own systematic mean, square that, and we can take the difference between each systematic mean and the overall estimate of the mean and square that. So now we have three different sum of squared differences, one within the systematic sample, one between the systematic sample, and one for the overall collection of observations. Why is this beneficial to us? Well, if you remember, when we first introduced systematic sampling, we actually noted that the SRS estimate of the systematic sample works best in the situation where we have no order or no periodic relationship between the values collected in the sample. So our systematic sample estimator, or rather the SRS estimator that we use when we are conducting systematic sampling, works best, or is the closest to the true variation estimate when we have a random population. But what if we actually want to use the true systematic sampling variation, or we want to compute the variance of the mean estimate across a systematic sample? So if we wanted to compute what is given in equation 6, well, we can actually get an estimate of the true variance of the mean by considering and calculating the components of the decomposition of the sum of squares that would fall out from the traditional one-way ANOVA. So given the layout of the data on the previous slide, we can formally write that our between sum of square difference is simply the square difference between each systematic mean and the overall mean, that the within sum of squares the within sum of square error is the square difference between each observation in its systematic sample and its corresponding mean. And then the total sum of squares is the difference between each observation and the grand mean of the entire experiment squared. So from this, we can actually build an estimate for the mean. So we can say that rho is equal to k minus 1 multiplied by n multiplied by MSB minus SST over n minus 1 multiplied by SST. And one thing that's a little bit, that could be potentially misleading here, in this context, we actually consider this n to be the n for each of the systematic samples. So this is really NSY subscript I, and this is really NSY subscript I. as well. Okay. So the purpose of arranging the data like this and considering these decompositions of the sum of square around the repeated systematic sampling value, or around the repeated systematic sampling estimates of the mean, is so that we can actually build an estimate for rho, which means that we could compute the true variation of our systematic sampling estimator. All right, so let's talk a little bit about what we can expect and then look at an illustration of this idea. Okay, so first, what can we expect? How do we believe that the variation estimate based off of a systematic sampling approach is going to act when compared to the true estimate? So in the first situation, we have what if MST is greater than MSB? Okay, so this means that rho is positive. Okay, and this means that the variation estimate of mu hat sy will act as an upper bound for the true variation. Okay. And then if MST is less than MSB, then we would have the opposite effect. So here we would have rho is negative, and we would have the variance of mu hat sy will act as a lower bound for the variance of mu hat sy. Okay, so a small mean square between, or a small mean squared error would be or a small variance between the means implies that the systematic seams are very close together. This is a pretty obvious statement. So this is basically just saying that if the variation between means is small, it just means that all the estimates are really close to each other based off of each repeated systematic sample. And that's a fairly intuitive conclusion. Okay, so if this is the case, we would want to choose to cluster to have similar means, but as much internal variation as possible. Okay, so if it's true that the MSBs is small, so if all the means are very close together, then we would want to have as much spread in the systematic sample as we possibly could. Okay, so let's look at an illustration of this idea. So this is a simpler illustration. Again, the textbook suggests that we collect 10 repeated systematic samples from a given population. But in this situation, for illustrative purposes, we'll consider a smaller scaled, oh, this is actually fine, a smaller scaled model now. So let's say we have 20 observations in the population. We have 4 systematic samples. Each systematic sample has 5 observations. Okay. So first off, let's complete the ANOVA table. So in this situation, we are visualizing our data in the following way. Okay, so we have observation, or right here, obs. So this would be like 1, 2, 3, 4, 5. And then here we would have the systematic sample. Okay. Right, so then you're going to have a Yij in each of the different entries, right? So you have 1 observation per systematic sample per observation slot. All right, if we consider an ANOVA, so a decomposition of the total variation across the whole scheme, the DF for the factor is going to be the number of systematic samples minus 1. So essentially each systematic sample is like a treatment group in this case. So The DF for factor is going to be the number of samples minus 1. So we can write here k minus 1, which is 3. And that's the standard degree of freedom for an ANOVA experiment. The next logical thing to do would be to find the DF for the total. So the DF for the total is actually going to be the population size in this case, minus 1. So we're going to have here capital N minus 1, which is equal to 19. Right, and then our error DF will be the difference between them, which is 16. And this would be the same thing as capital N minus K, which is 20 minus 4, which is 16. Okay, the mean squares are simply the sum of squares divided by their corresponding degree of freedom. So 42.2 over 3 is going to be 14.07. And 114 over 16 is going to be 7.13. Maybe I'll just write this out so that we have it here. So 42.20 over 3 and 114.00 over 16. Okay, so will the variance of mu hat sy act as a good estimate for the true variance? All right, so to answer this, what we can do is compute rho for this based off of this ANOVA table, and then use that to determine if this is going to act as a good estimate for the variance of the mean. So as a result, as a reminder, effectively what we would like is to see the rho as close to 0 as possible. So when rho is close to 0, this implies that our estimate of the variance of the mean from the systematic approach will be well estimated based off of a simple random sample estimate. So based off of an estimate that we would traditionally use in the systematic sampling approach. Okay, so here we can write, should have given myself a little more room, right? So B, so we compute rho. So rho is equal to, from the previous slide, so it's going to be k minus 1 multiplied by n multiplied by MSB minus SST, sorry, divided by n minus 1, or is it k? Just need to check that real quick. N minus 1 multiplied by SST. And this is 1d6.2. Okay, so here we're going to have 3 multiplied by 5 multiplied by 14.07 minus 156.2 divided by 5 minus 1 multiplied by 156.2. And this gives us 0.088. Okay. So now what we can say is, since rho is close to 0, we would expect our estimate for the variance to be a good estimator for the variance of mu hat. Right? So we can say, just need a little bit of room. Since rho is close to 0, it's not really approximately 0. We expect the estimate of the variance for mu hat to be similar, or to be close, I guess, to the true variance of mu hat sy, since the systematic sample should behave like a SRS. Okay. And then in the last part, it says, since there's no overlap between the 4 systematic samples, we have all of the information in the population. Use these values to find the true variation of mu hat sy. Okay, so we have the true variation mu hat sy is equal to sigma squared over little n multiplied by 1 plus n minus 1 times rho. Okay, so for sigma squared, we can actually just use MST. Why can we use MST? Well, we have all of the information in the population. So for all 20 elements in this population, MST is actually the squared difference between every single value within, is the square difference between each population element and the overall mean. So this is actually an estimate for sigma squared. So this is going to become MST divided by n. All right. And then we'll have 1 plus n minus 1 multiplied by rho. Okay, so then here we should have 156.2 over 19. Didn't do a very good job with the spacing on this one. Divided by 5, 1 plus 5 minus 1 multiplied by 0.088. And then this should be in the area of 1.0983. All right, so I think that this idea is actually pretty cool because, I mean, effectively what you're doing is, so we start with a systematic sample, we collect every kth point, and then we go, okay, like from our systematic sample of size little n, we can get an estimate for the mean and for the variation of the mean using our traditional SRS estimators. And then we say, okay, but what if from the population that we are interested in, we can collect repeated systematic samples? If we do that across all of the population elements, which is a stretch in some situations, but if we're able to do this across all population elements, then what we can do is construct a reasonable estimate for rho just by considering a decomposition of the total variation, which is what's being shown here. So in studying repeated systematic sampling, from what we have learned today, we have seen the general estimation procedure for the mean and then how to bound that estimate. And then this obviously extends to the total. We could do the same thing for a proportion as well, though we didn't look directly at those illustrations. Lost my train of thought there. Oh yeah, so for the repeated systematic sampling approach, we can do the same thing. We can bound our estimates for the mean and for the total in the traditional way using slightly different formulas. The mean estimate is basically the exact same thing. The variation estimate just takes the between variation across those repeated systematic samples directly. And then if we have all of the population information, we can actually consider the repeated systematic samples from the population to be structured like an ANOVA style situation. And in that case, as long as we don't have any overlap between the systematic samples, which shouldn't be an issue, we can then construct a reasonable estimate or construct an estimate for rho based off of the population information. And then we can compute the true variation for the actual systematic approach. But again, that would require we have all population information. All right, sorry, does anyone have any questions at this point? Probably just like, what are you talking about, right? Okay, so there's only one more topic I want to talk about in this lecture set, and then on Friday we can start the stratified stuff. So the last estimation procedure based off of a systematic approach. Okay, so this is called estimation based off of differencing, essentially, and the idea is as follows. So let's suppose that we have a simple random sample of y1 to yn. Okay. If our typical estimator for the mean, as we have seen before, is given here. So basically just the square difference between each value in the sample and the estimate of the mean. If the mean or the true mean is equal to 0, then our estimate of the variation is just given by the by the sum of each observation squared. Okay. And then we can say that from this, an unbiased estimator of sigma squared would be given by this quantity here. And that would be shown in a very similar way to what we had shown before when we had first done our calculations for the, when we had shown, I think on the assignment, that sigma squared hat is unbiased for sigma squared. Same idea here, except there's no mu to work with. So it would actually be a pretty straightforward calculation. Okay, so if mu is not equal to 0, what we could do is construct ND differences such that each difference is the successive difference between observation I plus 1 and observation I in the sample. And then what we can write based off the differences is that the expected value of the difference is equal to 0, and the expected value, or in the variance of each difference, is equal to 2 times sigma squared. Right? And then we can show that an unbiased estimator of 2 sigma squared, or an estimator for 2 sigma squared, is the sum of each difference squared divided by the total number of differences in the sample. And then if we do that, we can write that the variance of our estimate based off of our variance of the variance of the mean estimate is equal to 1 minus little n over capital N, 1 over n times 2 little nd times times the sum of the di squared. All right. Okay. So for a sample of size n, we typically construct n minus 1 differences, where di, again, is equal to the difference between successive observations in the data set. And then we write the variation as was shown before. So for example, the following table gives the number of births and the birth rate in the US population. Estimate the total number of births during this 41-year period and find an appropriate estimate of the variance. Estimate the mean birth rate during this 41-year period and find an appropriate estimate of the variance. Okay. So we have the following scatter plots for the number of births and for the birth rate. So the idea here is that you can see effectively for the number of births, this appears random. Okay, and then for the birth rate, we can see appears to be ordered. In particular, it is decreasing. Okay, so we have a random population, and then we have an ordered population. Total number of births, mean birth rate. Okay. And I think, sorry, I didn't state this clearly enough, but this differencing method is another way that we can use a systematic sample to construct an estimate for the mean and find an estimate for the variation of the mean in the situation where we do not have a random population. So in part A, we're asked to compute an estimate for the total number of births, right? So in part A, we want tau hat births. This population, based off the scatter plot here, we can see that these measurements don't appear to have any order. So they look random. So in this situation, we can just use our traditional estimates. But for the birth rate, there appears to be an order. So it's a declining population. So in that situation, we would want to use this differencing approach. Sorry, I should have made that clear before. So the differencing approach is a way that we can address the non-randomness issue with systematic sampling. Okay, but if we have randomness, we can just use the traditional estimates. But if we have an order, like a decreasing order here, this is a situation where we would want to use differencing. Okay, so this means use differencing, and this is use traditional. Okay, so here we're going to have tau hat bursts. All right, so this is going to be equal to capital N times mu hat bursts. So this is going to be capital N multiplied by 1 over little n times the sum I and s of each yi. All right. Okay, so from the question, we have a 41-year period. So capital N here is going to be 41 because each year constitutes a sample. Okay, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9 samples. Okay, so to estimate total bursts, we're going to sum from 36232 to 4158. So we're adding all of these values together. And then from that, what we're going to do is compute, or we're going to sum those together, divide by little 9, and then multiply by 41. So here we're going to have 41 times 1 over 9, and then we're going to sum from 36232 to 4158. And then this is going to give us 41 multiplied by 3,794.778, which gives us 155,585.9. All right. Okay, now if we wanted to bound the estimator, which I think is what we're asked for here, right? Find an appropriate estimate of the variance. Okay, so we can just use the systematic sampling estimator here to estimate the variance. So clearly this 1 minus 9 over 41 is going to be less than 0.95. So we use FPC. And then we can say appropriate, sorry, I'm just going to go a little bit over, appropriate estimate of variance mu hat sy is equal to 1 minus, or sorry, n squared, 1 minus little n over capital N times sigma squared hat over little n. Okay, so sigma squared hat here is just going to be the squared difference divided by n minus 1 of each observation in the sample minus the mean for the entire sample. So I didn't give this value in the slide, which was a bit of an oversight, but I'll just give it to you here. So this is going to be 41 squared, 1 minus 9 over 41. And then sigma squared hat is going to be 115,959.7 divided by 9. And then this should have been given. Though if it was an assignment or something like this, we could compute this pretty easily just using Excel or R or something like that. And then that would be 116,904,347. Okay, so ran a little bit over, started a little bit late, but I'll stop there for today. So on Friday, I'll finish up the repeated systematic sampling material by this using the last illustration of differencing approach, which is something we would use when the population is ordered in the context of a systematic sample. And then we're going to start talking about stratified sampling, which is the topic of lecture set 3. So hopefully by the end of the day, Friday, you'll be able to tackle I think there's 8 questions on assignment 2. There's either 8 or 9 questions. So by the end of the day, Friday, you should be able to do 75% of the assignment. So 6 of the 8 questions or 7 of the 9 questions, and maybe even get all of them done except for the last question, which is a sample size calculation within stratified sampling. So as always, if you guys have any questions, please let me know. Apologies for the late start. Hopefully next week I won't have any issues getting into the room. And if I don't hear from you, I will talk to you on Friday, and I'll try and have the quizzes done. My goal is always to mark within a week. So by the latest, I hope to have the quizzes done by Monday at the very latest, but hopefully I'll get them done before. Okay, so have a good one, and I will talk to you guys on Friday morning at 9.